Let's have a look at the following question. This deals with a part of rotation and also a part of dynamics. Physics students are performing a lab using a mass pulley system shown above. The diagram is towards your right. The cart has a force sensor attached to it, and the total mass of the force sensor and the cart is 1.2 kilogram. So here the force sensor and the cart have a combined mass M that is equivalent to 1.2 kilogram. The force sensor is attached to a 300 gram hanging mass. So this mass M is equivalent to 0.3 kilogram in SI unit. Hanging by a string that is placed over a pulley. When the system is released, a motion detector recording the motion of the cart produces the following velocity versus time graph. Here, from the shape of the velocity versus time graph, it is evident that the graph has, or the points plotted on the graph have a positive linear slope, and the value of this slope is found out to be mathematically equal to, we can take the 2 points as this and this, giving us the expression 3 by 2. This is from the equation of a line, which gives us slope M as equal to y2 minus y1, y2 minus y1 over x2 minus x1. The value of the slope is 1.5. This is exactly nothing but the acceleration A, which is equal to 1.5 meter per second squared. So we have answered part A, which asks us to calculate the acceleration of the cart. So acceleration of the cart A is equal to 1.5 meter per second squared. This value has been found out from the slope of the graph using the slope expression. Slope M is equal to y2 minus y1 over x2 minus x1, where x1 comma y1 and x2 comma y2 are points on the line. Moving ahead, assume that tension is the only horizontal force which is on the force sensor and the cart combination, and ignore friction. Calculate the tension of the string for this scenario. Here we understand that the only driving force for this body is tension T. Let's call it tension T. And for part B, we have tension T, the driving force, as the equivalent resultant force F, which is nothing but mass times acceleration. We have the values for mass as 1.2 and acceleration as 1.5, giving us the value of tension to be 1.8 Newton. Moving ahead, part C asks us or tells us that the measured tension is greater than the value predicted. Explain why this might be the case. The force sensor and the motion sensor are working properly, so do not use faulty data to explain the result. Since the explanation using faulty data is out of the picture, we can just tell that in reality, there is friction involved between the wheels of the force sensor and the cart combination and the surface of the table. Since friction is always involved in a realistic scenario, the actual value of tension measured will always be greater than the value theoretically found out, which is 1.8 Newton, since the driving force, which is tension in this case, has to overcome the frictional force between the surface of the table and the wheels of the cart. Moving on to part D, describe a process you could use to determine the rotational inertia of the pulley with this system, a meter stick, a force sensor, and a motion sensor. To understand and help answer this question, let us first write the free body diagrams for 3 bodies specifically: the pulley system, the force sensor, and the cart combination, and the hanging mass. So we can start with the pulley system. The pulley system has 2 tensions acting. Let's call the first tension as T1 acting in this direction because of the combination of the force sensor, and the cart. So let's call this T1. And the second tension is T2. It also has its own weight acting downwards. We'll call this weight W. And let's assume the system has a radius, capital R. There is also the normal force in this direction, Fn. Now, for the force sensor and the cart combination, we have the free body diagram denoted or depicted like this. Its weight is downwards. Its reaction force, either denoted by N or Fn, is upwards, and tension T1 is towards the left. For the third mass, the mass that is hanging, its weight is acting downwards as usual, and its tension T2 is acting upwards, and the resultant force is obviously downwards. So here, to perform the experiment, we can use a motion detector to measure these quantities. We can use it to measure the velocity v of the cart. We can also use it to find the acceleration a of the cart. And we can also use it to find that of the hanging mass, since that they are attached. Moving ahead, we can also use the slope of the graph, that is the slope of the velocity versus time graph, to find out the acceleration as stated before. And we can use the force sensor, to measure the tension T1. And we can use a meter stick to measure the radius of the pulley R. And with all these values, we can use Newton's law of rotation to find the subsequent answers. Now, let's start to apply Newton's second law. And when we apply Newton's second law, we know that torque tau is equal to moment of inertia I times angular acceleration alpha. This is the rotational equivalent of the translational equations F equals ma. Here force F is replaced by torque tau. A mass of a body m is replaced by moment of inertia I, because that is the rotational equivalent of mass. And linear acceleration a is replaced by angular acceleration alpha. A and alpha are denoted, or in fact related, by the relation A is equal to alpha times capital R, which helps us rewrite the equation as alpha is equal to A by capital R. We can find out torque as force into distance from the center, which is R. Since here we notice that T1 corresponds to a clockwise rotation, T2 corresponds to an anti-clockwise rotation, the resultant torque is T2 minus T1 times R is equal to moment of inertia I times A by R. Rewriting the equation such that we make moment of inertia I the subject of the equation, we get I equivalent to T2 minus T1 times R square divided by A. Thus, we can find out the moment of inertia I.